Have you ever really stopped to think about the sheer range of speeds in chemistry? I mean, some reactions are practically instantaneous. Think about fission, how quickly that happens, or photosynthesis.
Yeah, blink of an eye stuff.
Exactly. And then you have things on the other end, like iron rusting or diamond, very, very slowly turning into graphite over, well, ages.
Hmm.
How do chemists even begin to measure that huge difference, let alone control it?
It's a great question, and it gets right to the heart of what we're diving into today. Chemical kinetics. Basically, the study of how fast chemical reactions actually happen.
Right.
And it's not just, an academic exercise. Understanding this, how fast is fundamental. It impacts everything from how we design drugs to controlling pollution, even just cooking dinner.
Absolutely. So our mission today really is to unpack the key ideas from your sources, those textbook chapters and lecture notes, to get a solid grip on what makes reactions speed up or slow down. We want to look at the underlying mechanics, the sort of hidden factors that set the pace.
Exactly. We'll cover the main factors influencing rates, delve into collision theory, that molecular dance happening constantly, then look at how we actually measure these speeds. We'll also hit the crucial role of concentration and the sometimes counterintuitive effects of temperature.
And then finish up by looking behind the curtain at reaction mechanisms and how catalysts work their magic.
That's the plan. We'll get into all of that.
Okay, let's dive in then. Chemical kinetics, it sounds complex, but at its core, it's just the study of reaction rates, how fast reactants turn into products.
Simple definition, but yeah, the implications are huge. Take drug design, for instance. It relies heavily on kinetics, pharmacokinetics, that's the term for how fast a drug is, absorbed, distributed, metabolized, and finally eliminated.
Right. You can't just have a drug that works. It has to work at the right pace in the body.
Precisely. Get the rate wrong, and you either don't treat the condition effectively or you risk toxic buildup. It's all about timing and concentration over time, which is kinetics.
And you see this outside medicine too, right? Like in environmental science.
Oh, absolutely. Designing ways to speed up the breakdown of pollutants or maybe slow down reactions that form things like smog. Or think about food. You want fermentation to happen reasonably fast, but you definitely want to slow down spoilage.
Slow it way down, preferably.
Exactly. And in industry, making stuff faster often means making it cheaper and more efficiently. So controlling reaction rates is, critical for the bottom line.
So you mentioned four big factors influencing rates.
Yep. Generally, we look at four main things: the concentration of your reactants, the temperature, the physical state, specifically the surface area if you have solids, and whether or not a catalyst is present. We can break each of these down.
Okay, maybe start with why reactions happen in the first place. It has to do with molecules bumping into each other, right?
That's the core idea, yeah. It's called collision theory. For a reaction to occur, the reactant molecules generally need to physically collide. More collisions usually means a faster rate. Simple enough.
But it's not just any collision, is it?
No, absolutely not. That's the crucial part. We need what chemists call effective collisions. And for a collision to be effective, two conditions must be met.
Okay, what are they?
First, the colliding molecules have to have enough energy. They need a certain minimum amount of kinetic energy to actually break old bonds and start forming new ones. We call this minimum energy the activation energy, symbolized as Ia.
Like pushing a ball over a hill, you need enough push to get it to the top?
Exactly like that. If they collide with too little energy, less than Ia, they just bounce off each other unchanged. No reaction.
Got it. And the second condition?
Orientation. Even if they hit with enough energy, the molecules have to be lined up correctly relative to each other.
Ah, like fitting a key into a lock.
Perfect analogy. Your sources use the example of a chlorine atom, Cl, hitting a nitrosyl chloride molecule, NaCl. For them to react and form Cl2 and NO, that incoming Cl atom has to collide with the Cl atom that's already part of the NoCl.
If it hits the nitrogen or oxygen instead.
Nothing happens. It's an ineffective collision, even if the energy was sufficient. Both energy and proper orientation are required.
So when everything lines up enough energy, right, orientation, what happens at that exact moment of impact?
You momentarily form this very unstable, high-energy arrangement of atoms called an activated complex, or sometimes a transition state. It's like the ball perched right at the very peak of that energy hill, just before it rolls down the other side to become products. It exists for only an instant.
Okay, that makes sense. Now, how does temperature fit into this collision picture? We know heat speeds things up.
Right, and collision theory explains why beautifully. Higher temperature means molecules are moving faster, on average. So yes, they collide more often. That's part of it.
But not the whole story.
Not the whole story. The bigger effect usually is that at higher temperatures, a significantly larger fraction of the molecules possess kinetic energy equal to or greater than the activation energy, EA.
So more molecules actually have enough energy to make it over that hill when they collide.
Precisely. Your textbook likely shows this with those distribution curves, often a blue line for lower temp, red line for higher temp. The area under the curve past the E mark is much bigger for the higher temperature. More molecules capable of reacting leads to more effective collisions per second, and thus a faster rate.
Okay, so these collisions and energy barriers are happening at the molecular level.
Yeah.
How do we actually measure the result? How do we quantify the rate?
Good question. We can't see individual molecules, obviously, so we need to track some macroscopic property that changes as reaction progresses.
Like,
Well, if a reactant or product is colored, say, you're consuming reddish-brown bromine, you can use a spectrometer to measure how the color intensity, the light absorption, changes over time. As the bromine disappears, the color fades.
makes sense. What if there's no color change?
If the reaction involves gases, like hydrogen peroxide decomposing to produce oxygen gas, you can monitor the pressure change using a manometer. Or, if ions are being produced or consumed, you could measure the change in electrical conductivity of the solution.
So you track something measurable that correlates to concentration changes.
Exactly. And when we talk about the rate itself, we often differentiate between an average rate and an instantaneous rate.
What's the difference there?
The average rate is just the total change in concentration over a specific time interval. Like change in concentration divided by change in time becomes not...
But concentrations are always changing during the reaction,
Right.
right? So the rate isn't constant.
Exactly. The average rate gives you a picture over an interval, but the rate itself is slowing down as reactants get used up. That's why the instantaneous rate is often more useful. It's the rate at one specific moment in time.
How you find that?
If you plot concentration versus time, the instantaneous rate at any point is simply the slope of the line tangent to the curve at that exact point. It's like checking the car's speedometer at that precise second.
Got it. And you mentioned a rate constant, K.
Yes, K is the proportionality constant that links the reaction rate to the concentrations of the reactants. It's a specific value for a given reaction at a constant temperature. It sort of encapsulates the effects of activation energy and temperature for that reaction.
Okay, here's something that I remember being tricky. Dealing with the balanced equation. If you have, say, 2A plus B, C, A disappears twice as fast as B, right? How do you define the rate of reaction?
Ah, yes, the stoichiometry challenge. You're absolutely right. The rate of disappearance of A is different from the rate of disappearance of B. To get a single, unambiguous rate of reaction for the whole process, we normalize it.
Normalize how?
We divide the rate of change of each substance by its stoichiometric coefficient from the balanced equation. And crucially, for reactants, we put a negative sign in front because their concentration is decreasing, but we want the overall rate to be a positive number.
So for 2A plus BC, the rate can be expressed as 12, bait, or as D, or plus D. And those would all be equal.
Exactly. That standardization gives us one consistent value for the reaction rate, regardless of which substance we choose to monitor. It's a really important convention.
Okay, that clears that up. Now, this leads us to the rate law,
Yeah.
right? Which sounds pretty important.
It is. The rate law is the equation that explicitly shows how the reaction rate depends on the concentrations of the reactants. It generally looks like this. Rate equals X by.
Where K is that rate constant again. A and B are the concentrations.
Right.
What are X and Y?
X and Y are the reaction orders with respect to reactants A and B. They tell you how sensitive the rate is to the concentration of each reactant.
Now, the really crucial point here, the one that always gets emphasized, is that X and Y are not necessarily the same as the coefficients in the balanced equation, right?
Absolutely critical point. You
Yeah.
cannot, I repeat, cannot simply look at the balanced equation AA plus BBE products and assume XA and YB. The orders X and Y must be determined experimentally.
Why is that? Why don't the coefficients work?
Because the rate law reflects the actual step-by-step mechanism by which the reaction occurs, particularly the slowest step, not just the overall start-to-finish stoichiometry. We'll get more into mechanisms later, but for now, just remember, rate law exponents come from experiments, not the balanced equation.
Okay, experiment only. So
Why?
how do you do that experiment? How do you find X and Y?
You use the method of initial rates. You run the reaction multiple times, systematically changing the initial concentration of one reactant while keeping the others constant, and you measure the initial rate for each run.
How does that help?
Let's say you double the initial concentration of reactant A, keeping B constant. If you observe that the initial reaction rate also doubles, then the rate is directly proportional to A, meaning the reaction is first order in A, x1.
What if doubling A makes the rate 4 times faster?
Then the rate depends on A squared, so it's second order in A, x2. If doubling A had no effect on the rate.
Zeroth order, XX.
Exactly. By comparing how the rate changes when you change each reactant's concentration individually, you can figure out the exponents x and y. The sum of these exponents, x plus y, gives you the overall reaction order.
And that rate constant K, does it always have the same units?
Nope. Another tricky detail. The units of K actually depend on the overall reaction order. They have to adjust so that when you plug concentrations into the rate law, the final units for the rate always come out as concentration per time, like molarity per second, m's.
So for a first order reaction rate KAA, the units of K must be 1 time like that.
Correct. For a second order reaction, rate equal Ka, the units of K would be made by moy. They change to make the math work out dimensionally.
Okay, so rate laws tell us about initial rates and concentration dependence. What about predicting concentrations later in the reaction?
That's where integrated rate laws come in. They relate concentration directly to time. They are derived mathematically by integrating the rate law equation. They let you calculate the concentration of a reactant remaining at any given time t, or figure out how long it takes to reach a certain concentration.
Let's look at first order again. Rate law is rate equals Ka. What's the integrated form?
The most common forms are ln at a0, right 0, or rearranged. lnaa equals natch tt plus laa0. Here, a0 is the initial concentration, and at is the concentration at time t.
And that second form, LNA equals Natchez TT plus LNA0, looks like the equation for a straight line, y equals mx plus b.
It is. That's incredibly useful. If you plot the natural logarithm of the concentration, lnAt, on the y-axis versus time t on the x-axis for a first-order reaction, you get a perfect straight line, and the slope of that line is equal to LT. It's a great graphical way to find the rate constant.
And what about half-life for first order?
Half-life, T12, is the time it takes for the concentration to drop to half its initial value. For first-order reactions, the half-life is remarkably constant. It doesn't depend on how much you started with.
Really? So it takes the same amount of time to go from 1 molar to 0.5 molar as it does to go from 0.5 molar to 0.25 molar.
Exactly. And the equation is simple. T12 is 0.693 K. This constant half-life is why radioactive decay, which is a first-order process, is so useful for dating things.
Okay, what about second-order reactions? Rate law is usually rate equal Ka0.
For that rate law, the integrated form is 1A at equaled Ka plus 1A0. Again, this fits the y equals mx plus b format if you plot 1A, the reciprocal of concentration, versus time. You get a straight line with a slope equal to K.
And the half-life is a constant too?
No, it's not. For second-order reactions, the half-life depends on the initial concentration. T12 equals 1 Ka0. This means the half-life is longer as the concentration drops. If you start with less reactant, it takes longer for half of it to react compared to starting with more.
That's a key difference from first order.
A very important distinction. And briefly, there are also zeroth order reactions where rate IOK. The rate is constant independent of concentration. The integrated law is at mass KT plus A0, and the half-life is A0 2K. These are less common but pop up, especially in catalysis when the catalyst surface is saturated.
Okay, we've covered concentration effects pretty thoroughly. Let's pivot back to temperature. We know reactions generally speed up when heated. Is there an equation for that?
There is, and it's a cornerstone of kinetics, the Arrhenius equation. It quantifies how the rate constant K changes with temperature. It's K equals AE dash AR.
Okay, let's break that down. K is the rate constant, EA is activation energy, R is the gas constant, T is absolute temperature in Kelvin. What's A?
A is called the frequency factor or pre-exponential factor. It's related to the frequency of collisions and the probability that collisions have the correct orientation. It sort of bundles those factors together.
And the equation clearly shows that if EA is bigger, a higher energy barrier, the exponent becomes more negative, making K smaller, so the reaction is slower.
Correct. And if T is higher, the denominator RT gets bigger, making the negative exponent smaller, closer to 0, which makes e to that power larger, thus increasing T and speeding up the reaction. It mathematically captures our observations.
Can we use this equation practically?
Absolutely. You can rearrange it by taking the natural logarithm, lnk nish er 1t plus nna. Notice, again, this is the equation of a straight line, y equal mx plus b. If you plot lnk versus 1t using data from experiments at different temperatures, the slope of the line will be ni-ir. so you can determine the activation energy graphically.
Very neat.
There's also a 2-point version that lets you calculate E if you know K at 2 different temperatures, or predict K at a new temperature if you know E and K at 1 temperature. It's very useful for predictions.
And your sources mentioned tree crickets chirping.
Yes. It's a fun example. The rate at which some crickets chirp is strongly dependent on temperature, following the Arrhenius equation surprisingly well. It's a biological process behaving like a chemical reaction rate in terms of temperature dependence.
That's wild. Okay, so we know what affects the rate and how to measure it. But what about the actual step-by-step process? The balanced equation is just the start and end.
Exactly. That's where reaction mechanisms come in. The mechanism is the detailed sequence of elementary steps, individual molecular events that add up to the overall reaction. Think of the balanced equation as A to Z, but the mechanism is A to B, B to C, C to all the way to Z.
And these mechanisms often involve species that aren't in the overall equation.
Yes, those are called intermediates. They are produced in one elementary step and consumed in a subsequent step. So they exist during the reaction, but they aren't reactants or final products. Like N2O2 in the reaction between NO and O2, it's formed and then quickly reacts further.
You call the steps elementary. What does that mean?
An elementary reaction is one that occurs in a single step, exactly as written. We describe them by their molecularity, the number of reactant molecules involved in that single collision event.
So unimolecular means one molecule just breaks apart or rearranges.
Yep. Bimolecular means 2 molecules collide. Termolecular, 3 colliding simultaneously, is very rare because the probability is so low.
And here's the important bit for elementary steps.
Ah, yes. For an elementary step only, the reaction order for each reactant is equal to its stoichiometric coefficient in that specific step. If an elementary step is A plus B EP, its rate law is rate equals KAB. This is the only time you can get orders directly from coefficients.
Okay, so mechanisms are multiple steps. How does that relate back to the overall rate we measure?
In most mechanisms, one step is significantly slower than all the others. This slowest step acts as a bottleneck and determines the overall rate of the reaction. It's called the rate-determining step, or RDS.
Like the slowest worker on an assembly line setting the overall production pace.
Perfect analogy. The overall reaction can't go any faster than its slowest elementary step. So the weight law for the rate-determining step should match the experimentally determined rate law for the overall reaction.
So for a proposed mechanism to be considered valid, what needs to check out?
2 things. First, the elementary steps must sum up correctly to give the overall balanced chemical equation. Second, the rate law predicted by the rate-determining step must agree with the experimental rate law.
What if the slow step isn't the first one? And maybe there's a fast equilibrium step before it.
That happens. If you have a fast equilibrium step that produces an intermediate, and the intermediate is involved in the slow step, you need to use the equilibrium constant expression from the first step to substitute the intermediate's concentration in the slow step's rate law. You want the final rate law only in terms of initial reactants. It adds a layer of algebra, but it's necessary.
It sounds like figuring out mechanisms requires some detective work.
It really does. Rate data can only show if a mechanism is consistent or plausible. To really prove it, chemists need more evidence, like actually detecting those fleeting intermediates or using isotopic labeling, like swapping oxygen-16 for oxygen-18 to track where atoms go during the reaction. It's pretty clever stuff.
Okay, final big topic.
Yeah.
What if a reaction is just too slow? How do we speed it up, besides just cranking up the heat?
That's the role of catalysis. A catalyst is a substance that increases the reaction rate without itself being consumed in the overall process. It participates, but it gets regenerated at the end.
How does it work its magic?
It provides an alternative reaction pathway, a different mechanism, that has a lower activation energy than the uncatalyzed reaction. It essentially digs a tunnel through that energy mountain, making it easier for reactants to become products.
Lowering the barrier.
Exactly. You can see this clearly on potential energy diagrams. The catalyzed path has a lower peak.
But does it change the overall energy difference between reactants and products? Does it change the equilibrium?
Excellent point. No, it doesn't. Catalysts do not change the overall thermodynamics or the equilibrium position. They only affect the rate at which equilibrium is reached. They make the journey faster, but the starting and ending points remain the same.
Are there different kinds of catalysts?
Broadly, yes. We talk about heterogeneous catalysis, where the catalyst is in a different phase from the reactants, very commonly a solid catalyst with gas or liquid reactants.
Like in a car's catalytic converter.
Precisely. That's a perfect example. Solid metals like Platinum, palladium, rhodium coat, a honeycomb structure, and as exhaust gases flow over them, they catalyze reactions, turning nasty stuff like CO, NOx, and unburnt fuel into CO2, N2, and water. Maximizing the surface area of the solid catalyst is crucial here.
Makes sense. The reaction happens on the surface.
Right. Then there's homogeneous catalysis, where the catalyst is in the same phase as the reactants, usually all dissolved in a liquid solution. Many acid-catalyzed or base-catalyzed reactions in organic chemistry fall into this category.
And the third type, the biological ones.
Ah, yes, enzymes. These are amazing biological catalysts, usually protein molecules that facilitate the biochemical reactions necessary for life.
And they're known for being incredibly specific, right?
Extremely specific. Often, an enzyme will only catalyze one particular reaction involving one specific reactant molecule called the substrate. The lock and key analogy is often used. The substrate fits perfectly into the enzyme's active site. Although we now know enzymes can be a bit flexible too, the induced fit model.
And they're super efficient.
Mind-bogglingly efficient. They can speed up reactions by factors of millions or even much, much more compared to the uncatalyzed rate. Life wouldn't be possible without them.
Is there a limit to how fast an enzyme can work?
Yes. If the substrate concentration gets very high, eventually all the active sites on the enzyme molecules are occupied. The enzyme is saturated, working as fast as it possibly can. At that point, adding more substrate doesn't increase the rate. Further, the rate levels off, becoming zeroth order with respect to the substrate. It's limited by how fast the enzyme can process the substrate.
And understanding enzyme kinetics is obviously vital in biology and medicine.
Absolutely. Everything from metabolism to DNA replication relies on enzymes. Understanding how they work, how they can be inhibited or activated is fundamental to treating diseases and understanding physiology, like how the body processes alcohol, as you mentioned earlier, which involves specific enzymes.
Wow. We've really covered a lot of ground today, diving deep into chemical kinetics. We went from the basics of reaction rates and why collisions matter.
Through measuring rates, understanding rate laws, the impact of temperature via Arrhenius,
Then peeling back the layers to look at reaction mechanisms, the rate-determining step.
and finally how catalysts, including nature's enzymes, provide those crucial shortcuts to speed things up.
It really hammers home that these principles aren't just abstract concepts. They're actively shaping industrial efficiency, food preservation, drug development, environmental outcomes.
Everything around us, really. Understanding kinetics gives chemists the power not just to watch reactions, but to predict them, control them, design them for specific goals. Cleaner air, better medicines, even just a faster way to make essential materials.
It's incredibly powerful stuff. So, thinking about all this, what's an everyday phenomenon, maybe one we haven't mentioned, where you can really see the importance of how fast a chemical change happens? Something for our listeners to ponder.